let's talk about one other type of asymptote called a slant asymptote. So you know how when we had a polynomial, say y equals x squared over x minus 1, we would look at the numerator degree and the denominator degree, and then we'd say, okay, since the degree of the numerator is bigger than the degree of denominator, then we have no horizontal asymptote. But we have another kind of asymptote, not just a vertical asymptote at x equals 1, but also a slant asymptote. Let me just walk you through computing the slant asymptote for this one, and then we'll see what it looks like on the graph. So the way you compute the slant asymptote is actually a line that goes through, not a vertical line or a horizontal line, but a slanty line. So maybe it'll look something like this, and then maybe our function will sort of approach that going this way or going this way or something like that. So let's get rid of that picture for now because we don't know what the asymptote is for this one yet. So the way we compute the line is we do synthetic division on the polynomial. Well, in this case we can do synthetic division. Actually, let's just do long division because it's easier to see what's going on that way. So x minus 1 goes into x squared. Well, first term, x, because x times x makes x squared. So x squared minus x. Then we're subtracting that. So these cancel. And then minus a negative x, so it's a positive x. And then plus 1, because plus 1 times x is x. Then we subtract, these cancel, and then 2 plus 2 over x minus 1. So this right here, this is our slant asymptote, y equals x plus 1. So let's plot this. Oh wow, that looks really similar to the line that I drew before. Make it slope a little bit better. There we go. Okay, so that's y equals x plus 1. And then in order to plot our graph, well, we know there's a vertical asymptote at x equals 1. Because that's what makes the denominator 0. And then we just have to plot our graph. So what our graph ends up looking like is something like, let me try that again. Something like that. Something like that. In the next video, we'll talk about how to actually find the points for the graph. It's really just kind of plugging in points and seeing what it looks like. Like if you plug in 0, you get 0 for x, so you get 0 for y, so you know it's here. Then you can kind of infer what it's going to look like. We'll talk about that more, but for right now, the main finding that you need to know is that the way you find a slant asymptote is you do polynomial division, or synthetic division, whatever is appropriate, and then you take the non-remainder part, and that's your slant asymptote. So one thing you might notice is that in order to get a slant asymptote that's a line, like if this were an x cubed, then this first term would be an x squared. Then our slant asymptote would actually be a parabola, which would be a little bit less interesting because then it looks like it's just blowing up to infinity as usual. But to get a slant asymptote that's a line, you need the numerator to be degree 1 more than the denominator, exactly 1. And you can still think of a slant asymptote, like if this were x cubed and then we had an x squared as our first term as a parabola, you can still think of a slant asymptote like this. I guess it's not really a slant asymptote anymore because it's not perfectly like slanted, but it's still like an asymptote that the function is approaching. So in that case, we have kind of like a parabola asymptote, and maybe our function would look something like that. But the only one you're really going to be quizzed on in any kind of algebra setting is the regular line asymptote. So yeah, take away all this rambling. You just need to really worry about a slant asymptote when the numerator is 1 more than the denominator degree. And the degree of the numerator is 1 more than the degree of the denominator. Maybe I'll write that down just for emphasis. So, slant asymptote when degree of numerator is 1 more than degree of denominator. Yeah, so that's the only time you really got to worry about when you're drawing